Hi, Assalamualaikum. Today we would like to present the data that we have collected for our assignment. This project was conducted by a team of 5 members, Balkis, Christina, Zahra, Yusrina, and me, Amni. For introduction, Malaysia experienced a tropical climate characterized by high annual rainfall. However, recent decades have shown significant variation in rainfall distribution and dry periods, leading to extreme climate events such as severe flooding and prolonged droughts. This change pose a critical threat of the water resource, agriculture, and human activity across the country. The study aims to visualize and examine the spatial and temporal shift in Malaysia rainfall pattern over a 35-year 1995 until 2019. By utilizing QGIS to interpret the data across a different time intervals, we identify trends of excessive rainfall and drought supported by documented climate events. Ultimately, this analysis seeks to provide a clear understanding of the country, changing climate to better future mitigation efforts.
Our project is a comprehensive spatio-temporal analysis of Malaysia's climate patterns of spanning a quarter century from 1995 to 2019. To visualize this evolution, we utilize QGIS for spatial data processing and QGIS to web to develop interactive web-based map interfaces. Our primary objective is to classify rainfall patterns into 5-year intervals, allowing us to distinguish between periods of extreme drought and heavy precipitation. We aren't just relying on raw data, we are cross-referencing our findings with verified news archives to establish historical truthiness, ensuring our Pdsi models align with recorded national disasters like the Great Flood occurred in 2014 and drought between the year of 2015 and 2016. For each 5-year interval, we analyzed 3,311 individual data points across Malaysian landscape. This high-density datasets allows us to observe subtle changes in the Palmer Drought Severity Index (PDSI), providing a granular view of how climate stress moves across different states. By using such a large sample size, we ensure that our classification of moderate versus extreme weather is statistically robust and scientifically sound.
We use first and second tools to bring our data into QGIS. The first tool, which is delimited text, is for adding CSV file which contains coordinates in longitude and latitude. So the second tool, which is vector, is for our map boundary, such as Malaysia's boundary map. So we cannot analyze data until we connect what happened, which is our statistics, to where it happens, which is our map. Next, we use symbology tool, which is the visual style of our map, such as colors and also symbols. This feature can turn confusing numbers into colors that anyone can understand the data instantly without. Next, we use color ramp selector feature or tool, and this is the gradient of color which we use in our QGIS project. So this feature shows the intensity of the problem, such as red blue, which we use in our project, where red indicates drought and dark blue indicates heavy rainfall. So the viewers can immediately know where the hotspots are. Next, we use fixed interval tool, which we can group our data into equal chunks, such as 0 to 10 or 10 to 20. Next, we use IDW tools, which is a scientific guessing tool. It predicts the values of the areas where we don't have rain sensors, since some places does not have rain sensors. It fills in the gaps to create complete and smooth map of an entire region. Next, we use IDW parameters, which is distance coefficients that ensures how distance can affect our guess, and also cell size that ensures how sharp and detailed the map looks. So setting this correctly will complete the guess and complete the law of physics that things that are closer are more similar. Next, we use symbol size and transparency tools. These tools we use to make our icons smaller or bigger, and also making layers that are see-through. Size shows volume, while transparency is vital to show the base map, which shows the town underneath the data. Next, we use QGIS2 web plugin tool, which we can turn our QGIS project into a link that is accessible in any browser.
Alright, so now let's first go to the QGIS 3.44 version and create a new empty project. Alright, from here you must remember where you put all of your data in. As for me, I put it in home, in downloads, and in Balkis SEV folder. Alright, now from here you must first put the best layer first, which is the OpenStreetMap. The OpenStreetMap, and then we zoom into Malaysia, which is where our station going to be. Let's zoom a little bit more and add the data that I mentioned earlier, which is going to be the 0, 1, and 2. Okay, from here, add more layer, and then go to add delimited text layer. Make sure your data is in CSV format. Alright, put in the Pdsi 15 to 19. In the geometry derivatives, make sure the geometry CRS is the WGS 84, and X field is longitude, Y field is latitude. Click add and close it. Alright, now right click to the PDSI 15 to 19, go to the properties, and in the symbology, adjust first the single symbol to graduated one. Alright, select your value, which is going to be PDSI 15 to 19. The color, we decided to choose red to blue version. Alright, from here, you go to the mode and go to fixed interval. So from here, it allow us to insert the data according to the PDSI standard. Alright, from here, you are able to adjust the value and legend according to the standard from the journal or article. Alright, from here, after that, you right click to the symbol and adjust the opacity, and then from here we apply and decided to adjust a little bit more to the layer below the PDSI 15 to 19. This is according to your own liking. Alright, now we have finished it. Go to the processing and toolbox, search for IDW interpolation. Okay, now you have inserted. From here, make sure you identify your vector layer interpolation attributes, the distance coefficient. Okay, from here we accidentally missed one part, which is the interpolation attributes. So this is the result. Though it's a mistake, you can still redo it again by right click and remove the layer. Alright. Click OK and redo what I just mentioned. The vector layer, the attributes. Click plus button. The distance coefficient 2. The distance coefficient 2 is actually widely accepted in the environmental studies. Alright. The pixel size, make sure it is in lower version, because the higher it is, the slower it gets for it to process. So this is going to be the result. Though it looks very ugly, you can still adjust it to your own liking. Now you right click it and go to the properties and then adjust to single head pseudo color. Alright, from here do what I mentioned earlier in the PDSI 15 to 19. And now click apply and click. This is going to be the result. Okay. Now you want to deploy in web. Go to web, QGIS to web, and then export it. Just wait a little bit and you are done. This is going to be the result. That's all from me. Thank you. Alright. So now let's first go to the QGIS 3.44 version and create a new empty project. Alright, from here you must remember.
Here is the Pdsi scale. It provides a standardized measurement of moisture abnormality by balancing precipitation and temperature data. In QGIS, we visualize these values by using a diverging color ramp, where negative red values represent drought and positive blue values represent wet spells. This allowing us to identify regions experiencing long-term climatic stress relative to their local historical normal. And at the bottom, we can see the peer-reviewed table of the Pdsi classification. Looking at our 1995 to 2000 map analysis, we see a distinct tug of war between moisture surplus and deficits across Malaysia. Using Palmer Index, which is Pdsi classification, we can pinpoint exactly how climate shift impacted each region during this window. In the north, Kedah and Perlis maintain a steady moisture baseline. However, moving down the west coast and into Kelantan, we see a shift into severe wet conditions, likely driven by heavy monsoon surge. Conversely, the southern peninsula, specifically Melaka and Johor, began transitioning towards incipient dry spells, signaling the early drying effects that will later peak in the 1998 drought. In East Malaysia, we see a sharp contrast. Sarawak acted as a major catchment area, ranging from incipient to severe wet spells. Sabah, however, mirrored the southern peninsula, staying within the incipient dry to near normal range. This highlights Sabah's specific vulnerability to El Nino patterns, where Pacific moisture often falls short. In summary, while severe wet zone dominated the north, the dry signals in Johor and Sabah serve as early indicators of the historic droughts of the late 90s. This spatial analysis helps us visualize Malaysia's complex climatic transition. The previous map analyzes Malaysia's rainfall from 1995 to 2000, classifying regional moisture into spells. We can clearly see how different states reacted to two major events, which are the 1997 El Nino and the 1999 La Nina. In the north, Kedah and Perlis maintain a steady moisture baseline. However, Penang, Perak and Kelantan saw severe wet conditions. While 1997 brought drought, these regions experienced an intense rainfall recovery during the 1999 La Nina. This leading to significant flooding. Conversely, Johor and Melaka stay within the incipient dry range, reflecting the 1998 water crisis where rainfall dropped by nearly 50%. In East Malaysia, the contrast is stark. Sarawak remained a severe wet zone, consistent with its high annual rainfall. Sabah, however, mirrored the southern peninsula incipient dry trend. After the devastation of Tropical Storm Greg in late 96, Sabah suffered a severe El Nino drought that slashed rainfall by 37%, keeping the state in a dry to normal range. In summary, this 5-year window shows a nation in transition, it moving from the century worst drought in 1997 to a severe wet recovery by 2000. This data underscores how geography dictates vulnerability to global climate cycles.
Based on the map from 2000 to 2005, the spatial data distribution of rainfall in Malaysia show a clear difference between wetter and drier areas. Regions shown in the blue experience higher rainfall intensity, while red and orange indicate lower rainfall or drought-prone condition, but area represent moderate or average rainfall. Below in Peninsula Malaysia, higher rainfall was mainly concentrated in the central and southern region, suggesting wetter condition during this period. The northern region experienced relatively drier condition, while the white areas indicate stable or average rainfall. In East Malaysia, Sarawak generally show higher rainfall. In Sabah, northern and eastern parts show intensive low rainfall areas indicate drought. Overall, the map show an uneven distribution of rainfall across Malaysia. East Malaysia in particular shows a clear distinction between wet, moderate, and dry zone. This indicates that some areas are more exposed to drought while others face a higher risk of heavy rainfall and potential flooding.
So, this is the data visualization of rainfall distribution in Malaysia. Now, we focus on Peninsular Malaysia first. You can see that the northern part has near normal rainfall distribution, which is in Perlis and Kedah. This is the lower risk of flood. Next, we can focus on east coast of Malaysia, which is Terengganu, Kelantan, and also some parts of Perak and also Pulau Pinang. They has a slightly higher rainfall distribution that can lead to flood if the drainage system is not managed well. So, some parts of East Coast Malaysia, which is the Kelantan and also Terengganu, has a high rainfall distribution, while the central of Malaysia, which is Kuala Lumpur, Selangor, and also Putrajaya, has also high rainfall distribution. Other than that, Negeri Sembilan, Melaka, and also some parts of Johor also experience high rainfall distribution. In central Malaysia, which is Kuala Lumpur and Selangor, has a very well-managed drainage system. So, during that time, central of Malaysia does not experience flood. Now, we can focus on east of Malaysia. The right side of Sabah and also the upper side of Sarawak has a slightly higher rainfall distribution, while the left side of Sabah and also the lower side of Sarawak has a high rainfall distribution, which is at risk of flood.
Looking at this map, you will notice the entire map is dominated by blue hues, classifying the 2010 until 2050 interval as extremely wet. However, it is better to understand the technical nuance behind this visualization. While Malaysia did experience dry spells during these years, our 5-year average is heavily skewed towards the wet spectrum. This is because the volume of rainfall during the year-end monsoons, particularly the catastrophic 2014 event, the Banjir Kuning event, was so immense that it statistically overwhelmed the dry periods. In GIS terms, the extreme precipitation anomalies at the end of the interval create a high positive bias in our Pdsi map, making the entire period appear permanently wet on a macro scale. On this slide, we bridge the gap between our blue map and the ground reality. Although the map shows a wet trend, our historical validation reveals a drastic transition actually. At the year 2010 and 2011, you can see there's a strong La Nina that remarks the higher average rainfall. Marking at late 2010, at Kedah and Perlis, there's a massive flood. Switching to 2012 and 2013, this year remarks the rainfall pattern slightly normal, but the flood occurred at the end of the year, but it's still balance of positive moisture balance lah. But heavy rains caused flooding in December 2012 and early January 2013. And due to the heavy rain on December 26, it had forced thousands of residents to evacuate, especially in Terengganu, Pahang, and Kelantan. And on 2014, well, this is the most immense event happened, the big flood, or you call it just Banjir Kuning. Uh, it was so devastating, involving 5 states in Peninsular Malaysia that experienced severe flooding, and Kelantan got affected the worst. That forced almost 230,000 people to evacuate from their houses. And technically, in early 2014, there was a slightly brief drop, but the event occurred, the flooding occurred very severe that the data of PDSI skewed the result, making it very extremely wet because of the Banjir Kuning. And at the beginning of 2015, I'm sorry, the second of 2015 is the beginning of the strong El Nino actually. But yeah, the average of this marks a very skewed data on rainfall and heavy flood that the data of PDSI skewed the result to extremely wet, marking almost no drop that happened in between this 5 year interval. And the extremely wet data peak aligns perfectly with the 2014, which is the Banjir Dahsyat lah, where the East Coast reached a maximum PDSI of 3.58. But as we move to late 2015, the climate flipped lah. Despite the blue visualization, the ground reality shifted towards a severe El Nino-driven drought. The reason our map remains blue is due to the temporary resolution. The sheer volume of water from the 2014 floods masked the onset on the 2015 drought in the 5 year average. This teaches us a critical lesson in the climate analysis, and the extremely wet interval can often the precursor to an extreme drop. And our study captures the moment right before that dramatic pendulum swing.
Alright, so this is the PDSI map for the period 2015 to 2019, which shows a clear spatial difference in moisture condition across Malaysia, where it display a blue that will indicate wet and red indicate dry and drought condition. The visualization shows that the weather conditions are more dominant in the east of Malaysia and western part of Peninsular Malaysia, especially in Selangor, Melaka, Perak, Kedah, and Pulau Pinang. Right, so just as shown in this graph, it shows that the number of flash flood occurred frequently in Selangor and Pulau Pinang, where a majority of the event considered as PFFs, which is the pluvial flash flood that usually occurred in urban area. So why does this PFFs occur in the first place? Is because the precipitation or the raining itself surpasses the capacity of the drainage system in the area either naturally or artificially. Alright, so while in Sarawak, it also recorded a flood, for example, in the February 2016, where the flood causing a landslide to occur in district of Serian. And this flood has affected 10,000 people, according to Malaysia Disaster Management Authorities, with 7,000 people has to evacuate from the location and a person died in the event. In contrast, the drought event that dominantly occurred in Johor, which is here, was expected to be the El Nino phenomenon, which occurred in 2016, where March and April recorded and happened to be the driest month. Alright, so therefore, Tariq et al. 2024, he suggested that the implementation of mitigation strategies must be done thoroughly because these flood and drought may have greater potential to trigger a great negative problem more in the future. That's all from me. Thank you.
To conclude, our 25-year study data reveals a critical shift in Malaysia's landscape. While we are a high rainfall nation, our data shows a move away from predictable weather towards a volatile seesaw between two extremes, which are excessive water surplus and severe scarcity. Our analysis across 5 intervals show a clear erratic cycle. We transitioned from severe wet in the late 90s to a severe drought warning in the early 2000s. This was followed by a decade of intensified moisture. It's peaking at extreme wetness between 2005 and 2015, before swinging back toward moderate drought from 2015 to 2019. This cycle proves our climate is not just changing, but it is become more unpredictable. This data directly reflects our national history. Our extreme wet classification aligns with the devastating 2014 Great Flood, while the recent drought phase matches the record-breaking 2016 El Nino. This correlation validates that our QGIS spatial modeling accurately captures the truth of Malaysia's climate journey. Ultimately, the normal average is disappearing. We must now prepare for a dual-threat reality, which are building infrastructure for extreme floods while ensuring water security for droughts. Understanding these 25 years of data is the first step toward a resilient Malaysia. Thank you.